So in the previous lesson, you learned how to quantify the change in total energy, or delta E, right? So delta E is equivalent to Q plus W, and Q is heat and W is work. And you also learn how to quantify heat, which is basically equivalent to mass times the specific heat capacity times change in temperature. In this lesson, you're going to learn how to quantify work. And in thermodynamics, there's a lot of different types of work. But in this chapter, you're going to learn how to quantify pressure volume type of work. So what is this pressure volume type of work? In thermochemistry, we're always dealing with chemical reactions. And these chemical reactions are the systems. It's basically what we're studying. In automobile engines, this pressure volume type of work occurs when the force is caused by a change in volume against an external pressure. And so basically in a car engine, you're injecting fuel or gas fuel into the cylinders. And then the fuel gets burned in the process, which is basically a type of combustion reaction. So this combustion reaction generates pressure. And this pressure results in the expansion of the volume. And when that volume expands, the pistons inside the cylinder moves up and down because of this change in pressure. And so that's basically how automobile engines work. You also learned in the previous chapter, or maybe in physics, that work is equivalent to force times distance. And you also learned in the previous chapter regarding gas laws that pressure is the force exerted per unit area by the gas molecules. And so pressure is equivalent to force divided by area. Now, if we rearrange this equation and isolate force, we can substitute it into this formula for work, right? So let's isolate F and then substitute that into this equation. And what we have is a new equation for work, which is pressure times area times the distance. And in automobile engines, the cylinders contain the pistons move up and down, right? And so this is the change in distance that we're talking about. So it's essentially the height of that piston moving up and down. And so now we have a new equation here for work, which is pressure times area times the change in height. Now, if you look at this area times change in height, or area times height, this is basically volume. Area times another distance is volume. And so work in that case is pressure times delta V, or the change in volume. Volume expansion means that the system or the chemical reaction itself performed work. Because remember that inside the cylinder, you're burning fuel, and that's a chemical reaction. And so because the chemical reaction resulted in the expansion of volume, it's basically pushing on that piston up, right? And so it's the system, the chemical reaction itself, that's performing work. And because of that, we put a negative sign in front of the equation or the formula. So now work is equal to the negative external pressure times the change in volume. So this is the equation for work. The negative sign just indicates that you have a volume expansion, and it's usually the system that's performing work. If you have a positive work, then that means that the surroundings performed work on the system. So in that case, if we have a compression, then that means we have a positive work, meaning the surrounding performed work instead of the system. But if you have an expansion, that means the system performed work. So it's just a sign convention. But make sure that you remember the sign convention regarding work, heat, and delta E, which is the total change in energy. All right, so let's look at an example here. To inflate a balloon, you must do pressure volume work on the surroundings. If you inflate a balloon from a volume of 0.1 liter to 1.85 liter against an external pressure of 1 atmosphere, how much work is done in joules? Okay, so how do we even approach this type of problem? Well, let's extract out the information. And so this is basically what's given. So we have initial volume. The initial volume is 0.1 liter. And the final volume is 1.85 because we're inflating a balloon, right, with an initial volume of 0.1 and then a final volume of 1.85. And we also know the external pressure, the pressure of the surroundings, right? It's 1 atmosphere. So how do we calculate the total amount of work that was performed on this balloon? In other words, how much work did you do in order to inflate this balloon from 0.1 liter to 1.85 liters? Okay, so you're the system, the balloon is the surroundings. So we know the equation for work. Work is basically equivalent to the negative external pressure times the change in volume. We have the external pressure, we have the initial and the final volume, so we can just calculate delta V and plug in all the numbers. So delta V, or the change in volume, is equal to 1.85 minus 0.1. So that gives us 1.75 liters. And then plug this into the calculator or to the equation. We have work is equivalent to negative 1 atmosphere times 1.75 liters. Okay. So that's equivalent to negative 1.75 liters atmospheres. Now, this is not joules. It's asking for joules. We can convert this into joules by using the conversion between them. So converting this is 1 liters atmospheres is equivalent to 101.3 joules. And so converting it to joules, we get negative 177 joules. So you performed a total of 177 joules because you're the system. So the next concept that I want to talk about here is called enthalpy. And enthalpy, by definition, is the heat evolved at constant pressure in a chemical reaction. And the symbol for enthalpy is capital H. And enthalpy H is equivalent to the internal energy or the total energy plus P times V. But enthalpy is actually a state function. So a state function means that you can't really measure it directly. You can only measure the change in the enthalpy. In other words, you can only measure the delta H, right? The difference in the final and the initial states. And so delta H then, or change in the enthalpy, is equivalent to the change in energy, delta E, plus P delta V, okay? Because it's the change that we're looking at. And so we also know what delta E is. Delta E is equivalent to Q plus W. You learned that earlier. And so if we plug this into this equation, then work is equivalent to negative P delta V, and plugging it in back into this equation for the change in enthalpy, the work basically cancels out. And what's left is heat. And that's basically the definition of delta H. The change in enthalpy is the heat evolved at constant pressure in a chemical reaction. And so the P here is a subscript, which basically tells you that delta H is the heat that was released at constant pressure. Okay, so this doesn't mean that you're multiplying heat by pressure. Okay. So when we have a positive delta H or positive enthalpy or change in enthalpy, that means that we have an endothermic reaction, an endothermic chemical reaction, which means that heat is taken in by the system, or the heat is absorbed by the system, by the chemical reaction. When we have a negative delta H, then we have an exothermic reaction, meaning that heat is given off by that chemical reaction as a system. So let's say that you dissolve sodium hydroxide, right, in water. Sodium hydroxide dissolving in water generally releases heat. And so that's right there is an exothermic type of reaction. So let's look at a few examples here. Identify each process as endothermic or exothermic and indicate the sign of change in enthalpy, delta H. So the first one here says the sweat evaporating from skin. So first you have to determine which one is the system and which one is the surrounding, so that you can see how heat is being transferred. Is it transferring out or transferring in? So sweat evaporating from skin. So the sweat would be the system because it's on your skin. It's absorbing heat, and then it evaporates in the process. So if you're treating sweat as the system, then it would be an endothermic process because the sweat is absorbing the heat from your skin. Okay. The next one here is water freezing in a freezer. Okay. So you put water into the freezer. In order for water to freeze, you have to remove energy. You have to remove heat from water. So if you're treating water as a system, then this would be an exothermic process because water has to release heat in order to freeze. And last one, wood burning in a fire. So when you burn wood, right, it releases heat, and you can feel it emanating from the burning wood, right? So that's pretty straightforward. That's going to be an exothermic process. Heat is released whenever you're burning wood. So how do we relate delta H, or this change in enthalpy, into chemical reactions, right? So we have to combine delta H and stoichiometry, because stoichiometry is it's a big part of chemical reactions. So delta H of reaction would be the heat that's released in a chemical reaction, or heat that's absorbed by a chemical reaction. So we call this enthalpy of reaction, or simply heat of reaction, because this is basically the heat evolved at constant pressure. We can also define this as the amount of heat produced and is dependent on the amount of reactants. All right, so the amount of heat that's released will depend on how much reactants you started out with. So let's look at this one example here. So this is propane gas. Okay, so when you burn propane in the presence of oxygen gas, you generate carbon dioxide and water. And the total amount of energy that's released by this system, this chemical reaction, is 2,044 kilojoules. All right, so the negative sign tells you that that's the amount of heat released and not absorbed. And so that's a lot of energy. So in terms of stoichiometry, what does this mean exactly? Well, this means that for every 1 mole of the propane gas, this will generate 2,044 kilojoules of heat. So 1 mole. How do we know it's 1 mole? Well, it's because of the coefficient right here. All right, there's a coefficient of 1. So for every 1 mole of the propane gas, it will generate 2,044 kilojoules of heat. And you can also use the other chemicals here in this balanced chemical reaction equation. So you can say that for every 5 mole of oxygen gas, based on this chemical reaction, that will generate 2,044 kilojoules of heat. You can also say for every 3 moles of carbon dioxide generated, this will release 2,044 kilojoules of heat, and so on and so forth. So we can turn this into a conversion factor, right? Where you have 1 mole of propane for every 2,044 kilojoules. So this is just a ratio between the moles of propane and the amount of heat. Or you can do the inverse, energy per moles of the propane. Or again, as I mentioned, you can use oxygen gas relative to the energy and vice versa. So let's look at this example here. A liquefied propane gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all of the propane in the tank. And it gives you the reaction equation here and the amount of heat that's generated by that chemical reaction equation. So the first thing that you want to do here is to write down what's given, right? So we have 13.2 kilograms of propane. And then we would convert this amount of propane into grams, and then from grams to number of moles. Once we've identified the number of moles of propane that we have, then you can just multiply that by 2044, and that basically converts moles of propane into amount of heat that's generated. Okay, so this is what's given. We have 13.2 kilograms of propane, and we have the amount of heat of reaction per mole of propane. And so we're going to convert mass to moles, and that gives us so the first part here of the dimensional analysis converts 13.2 kilograms into grams, so kilograms would cancel out, and then dividing it by the molar mass of propane gives us the number of moles of propane. So you can see that the grams would cancel out, and then use the relationship, the ratio between the number of moles of propane and the amount of heat that's generated. So we would put moles at the bottom and then the amount of heat generated up top. So all the units would cancel out, and we're left with kilojoules. So plug everything into the calculator. 13.2 times 1,000 times negative 2044 divided by 44, and we get negative 6.13 times 10 to the fifth power kilojoules. So that's the total amount of heat that's generated by this equation or chemical reaction with 13.2 kilograms of propane. So experimentally, how do we quantify this delta H of reaction, or heat of reaction, or enthalpy of reaction? How do we experimentally quantify this? Well, there's a lot of different methods that you can use in quantifying the amount of heat that's released from a chemical reaction. One of them is this method called constant pressure calorimetry. And this is pretty basic. Of course, there's a lot more advanced and more sophisticated methods out there, but there's constant pressure calorimetry, and there's also bomb calorimetry. But in this semester, this lecture, we're only going to cover constant pressure calorimetry. So in this type of method, we use a coffee cup calorimeter. So this is something that you can just make and build your own. It measures the delta H of reaction at constant pressure. So constant pressure meaning the external pressure, okay, the pressure that you can measure right now, atmospheric pressure. So this is what the setup would look like. You have two styrofoam cups that are nested, okay, and then you have this stirring rod to make sure that heat is circulating and evenly distributed in the solution. And then you have a thermometer that basically measures the temperature, the change in temperature within that chemical reaction. And so you have a chemical reaction happening here. So you would determine the initial temperature before the chemical reaction happened, and then measure the temperature again after or during the chemical reaction. So in the previous slides, you learned that the heat of reaction is basically equivalent to the heat generated by that chemical reaction at constant pressure, right? So delta H, enthalpy of reaction, is equivalent to Q at constant pressure. So how do we measure delta H of reaction? Well, if we can measure the amount of heat that's generated, that's your delta H, your enthalpy of reaction. So in that case, Q reaction, the heat that's generated by the chemical reaction, is equivalent to the heat that's absorbed by the solution, right? So this is in water, usually. So a lot of chemical reactions happen in water. And the heat that's generated by the chemical reaction itself will be absorbed by the water because the reaction is in water. And so in that case, Q reaction equals negative Q solution. So again, the negative sign just tells you that one is being absorbed and the other one is being released, right? It's basically like, so it's basically similar to determining, let's say, the force that a boxer releases through a punch by measuring the force that was taken by, let's say, a punching bag, right? So it's like an indirect type of measurement. So and we know the equation or the formula for heat. Heat, or Q, is equivalent to mass times the specific heat capacity times the change in temperature. And so if we know the specific heat capacity of the solution, we know the mass of the solution, we can measure delta T, and that's basically equivalent to Q reaction. All right, so at constant pressure, delta H, or the heat of reaction, is equivalent to Q reaction. All right, so let's look at an example here. Magnesium metal reacts with hydrochloric acid according to this balanced chemical reaction equation. Solid magnesium reacting with hydrochloric acid releases hydrogen gas and magnesium chloride. In an experiment, to determine the enthalpy change for this reaction, 0.158 grams of magnesium metal is combined with enough hydrochloric acid to make 100 milliliter of solution in a coffee cup calorimeter. The hydrochloric acid is sufficiently concentrated so that the magnesium completely reacts. The temperature of the solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius as a result of the chemical reaction. Find the delta H of reaction for the reaction as written. Use 1.00 gram per mil as the density of the solution and the specific heat capacity 4.18 joules per gram degree Celsius as the specific heat capacity of the solution. So how do we even approach this type of problem? Well, we can extract out all the information that we need, right? We have the chemical reaction equation here and it's balanced. We know the volume of the solution, given 100 milliliter of solution. We can determine the mass of the solution, the total mass, because we're given the density, right? You have 1 gram per mil as the density of the solution. Multiply that by 100 milliliter, we have the mass of the solution. So remember that the delta H of reaction is equivalent to Q reaction. So if we can determine Q reaction, we have delta H of reaction, right? And Q is equivalent to mass times the specific heat capacity times the change in temperature. We have heat capacity here, 4.18, and we have the change in temperature. It rises from 25.6 to 32.8. We can calculate the change in T. All right, so let's take a look. So this is all the information that we have, and that's all we need to answer this question. So the first thing that you want to do is convert the mass of magnesium into moles of magnesium, because what we're trying to find here is the heat generated per mole of magnesium. So we have to divide it by the amount of moles of magnesium. And so we're going to convert that to moles first. And then we can calculate the mass of the solution by multiplying the volume of the solution times the density of the solution. And then we can determine the change in temperature of the solution by taking the difference between the two numbers here. All right, so here we go. So Q reaction then is equivalent to the heat that's absorbed by the solution. So Q reaction equals negative Q solution. So that's negative mass of the solution times the specific heat capacity of the solution times the change in temperature of the solution. And we can just plug in the numbers here. So 100 grams for the mass of solution, because we just multiplied 100 milliliters by the density, 1 gram per mil. And this gives us negative 3.0 times 10 to the third joules. Okay, but usually this delta H of reaction is reported in kilojoules per mole, right? So that means that all we have to do now is divide this amount of heat by the moles of magnesium. All right, so dividing 0.158 by the molar mass, 24.31 grams, and then divide the heat by the result gives us negative 4.6 times 10 to the fifth power joule per mole of magnesium. Or if you want to convert this to kilojoules, that would be negative 4.6 times 10 to the second power kilojoules per mole magnesium. So a lot of chemical reactions have been studied, and their delta H of reactions have also been determined. And so let's say that you want to perform a specific chemical reaction. All you have to do is look at a list of chemical reactions and their respective delta H of reactions. And by combining these chemical reaction equations and their delta H of reaction, you can predict how much heat will be generated or how much heat will be absorbed by that specific reaction that you want. So let's take a look at how we can do that. If a chemical reaction equation is multiplied by some number n, then the delta H of reaction is also multiplied by that same number, that multiplier. So let's look at an example here. Let's say that we have this chemical reaction A plus 2B turning into chemical C, right? And the delta H of reaction for this reaction is equal to X, okay? Some random number, X kilojoules. Now, if we multiply this chemical reaction by 2 and we get 2A plus 4B equals 2C, then we would multiply the same number to the delta H, right? So now the delta H is equivalent to 2X kilojoules. Number 2, if a chemical reaction equation is reversed, then the delta H reaction changes sign from, let's say, negative to positive or positive to negative. You're basically reversing that chemical reaction. So let's say that you had originally a combination type of reaction, but now you're doing the reverse, which is decomposition type of reaction. How would that affect the delta H of reaction? Well, according to this, all you have to do is reverse the sign from positive to negative or negative to positive. Here's an example. A plus 2B turning into chemical C, and this generates X kilojoules. If we reverse this reaction, right now we have C and decomposing it into A and B, then all you have to do is turn the positive X into negative X. So negative X kilojoules. And another one here, the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. Okay, so the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So you're basically adding up all the delta H of reactions, and that becomes the delta H of reaction of a stepwise process. And this is known as Hess's Law. So for example, if we have A plus 2B turning into C, and this is the delta H of reaction for this specific chemical reaction, and then let's say we have another chemical reaction, C turning into 2D, and it gives you a value for its delta H of reaction, and that's equivalent to Y kilojoules. What would be the delta H of reaction for this specific chemical reaction equation? Well, is this something that we can get based on the given chemical reaction here? Well, if you add the two chemical reactions, 1 and 2, what you get is this chemical reaction equation, because the C's will basically cancel each other out. All right, so now you have A plus 2B turning into 2D, which is the chemical reaction that we want. Because we added the two chemical reactions, we would do the same thing for the delta H's. So in other words, delta H for this new chemical reaction equation is simply X plus Y. All right, so we have X plus Y kilojoules. So let's look at an example here. So let's say that we have this chemical reaction equation. We have three different chemical reaction equations. And we're trying to find the delta H of reaction of this specific chemical reaction equation shown here. So how do we solve the delta H of reaction for this reaction given the delta H values for these reactions here? So first we'll look at the source of carbon in the chemical reaction, source of hydrogen gas, source of propane gas, C3H8. So for C3H8, you can see that it's on the product side. So we want propane to be on the product side. In this chemical reaction here, propane is on the reactant side. So we would have to flip this reaction. We would have to reverse this chemical reaction equation. So if we reverse this chemical reaction equation, we would also reverse the sign from negative to positive. So again, we would reverse equation 1, this one right here. And as a result, we would also flip the sign from negative to positive. And that's basically what we've done here. We reversed equation 1. Now it's 3 carbon dioxide plus 4 water generates propane gas and 5 oxygen gas. So because we flipped the equation, we're also going to reverse the sign from negative to positive. The next one here is the carbons, right? So we see that in this chemical reaction, the carbon is on the reactant side. And so looking at these 3 equations, we would use equation number 2. And you see that there's supposed to be 3 moles of carbon. So we're going to multiply the second equation by 2 in order to match this, multiply by 3 in order to match this number of carbons on the reactant side. And because we multiply this by 3, we'll do the same thing for the delta H of reaction. All right, so as you can see here, we multiplied reaction number 2 by 3. So now we have 3 carbons, 3 oxygen gas, 3 carbon dioxide gas. And the delta H was also multiplied by 3. And for the last one, we would multiply it by 2 because of the fact that we have 4 hydrogen gas on the reactant side. And here we only have 2. So we would multiply this entire equation by 2. And so does the delta H of reaction. So now when we add up the chemical reaction according to Hess's law, the sum of the delta H's would be the delta H of reaction for this reaction equation shown here. So let's do that. So you can see that the 3 carbon dioxides will cancel out because this is on the reactant side and this one is on the product side. And then we have 4 water over here and 4 water over here as well. So those will 2 cancel. The oxygens will also cancel out. You have a total of 5 here on the left, 5 on the right. And what you have is the chemical reaction that you want, which is 3 carbons plus 4 hydrogen gas equals propane gas. All right, so all you have to do now is add up all the delta H of reactions, and we get negative 105 kilojoules. So this chemical reaction here will generate 105 kilojoules. So another way to calculate the delta H of reaction or heat of reaction is by looking at the standard heat of formation, which is delta HF. The degree sign there tells you that it was done under standard conditions. Okay, so this is the standard enthalpy of formation, or also known as standard heat of formation. So how do we calculate this from the standard enthalpy of formation? So how do we identify the delta H of reaction from standard enthalpy of formation? Well, these standard enthalpy of formation values are already calculated and predetermined from a given table. So you can just look at the delta HF values from a given table to calculate the delta H of reaction, or standard heat of reaction. And so we have the standard heat of reaction, which can be determined from standard heat of formation. And again, you're going to be this table is going to be provided to you on the day of the test. So let's look at a few examples. Pure elements are typically given a delta H of formation equivalent to 0 kilojoules per mole. Carbon dioxide gas is given the value negative 393.5 kilojoules per mole. Again, these are in their standard states or standard condition. So let's look at an example and how we can use a given table to calculate the delta H of reaction. All right, so for this one, calculate the delta H of reaction or standard heat of reaction for this chemical reaction equation shown here. So we have the combustion of methane gas in the presence of oxygen, and this generates carbon dioxide and water. And this is already a balanced chemical reaction equation. So all you have to do now is look at the delta HF values for every single one of these compounds involved in this chemical reaction. So oxygen will typically have a 0 kilojoules per mole. So let's look at the table. So here we can look at the values of, so this is basically the table of heat of formation. And so you can look at CH4. Hold on. So are we looking at CH4? Hold on one second. Yes. So CH4 is methane. And so you can see the value of delta H of formation. It says negative 74.6. So if you're forming or synthesizing methane, CH4, then the value is negative 74.6. And then we also have the value of carbon dioxide gas. If you're creating carbon dioxide, that would generate 393.5 kilojoules per mole. We also have the value of oxygen gas and the value of water vapor. So we can use all that information to calculate the delta H of reaction for that chemical reaction. So here's the chemical reaction equation again. You can see that we're basically burning methane and forming carbon dioxide gas and water. And so the value of methane is going to be negative 74.6 kilojoules per mole because of the fact that CH4 is on the reactant side. So when it says delta H of formation, it has to be a combination reaction type where you're synthesizing or you're forming methane. And so we're going to reverse the equation, so the reaction equation, and so we would reverse the value of the heat of formation from negative to positive. And then we don't have to worry about oxygen gas. That's basically 0. But then we have formation of carbon dioxide gas, and that gives us negative 393.5 kilojoules per mole. You're basically creating carbon dioxide from elemental carbon and elemental oxygen gas. For methane, it's elemental carbon and elemental hydrogen gas. And then the last one is for water, right, H2O. And so you can see that this is for 1 mole of water, but it says we're supposed to have 2. So we're going to multiply this by 2 to match what we have up here. All right, so that's basically what we did here. We multiplied it by 2. So we're going to look at equations 1, 2, and 3 to calculate the delta H of reaction based on the delta H of formation. So we're going to ignore this equation right here because we have now multiplied it by 2. So then we're going to add up all the equations and their delta H of formation according to Hess's law. So the carbons would cancel out. And then we have the hydrogen gas is canceling out as well. So you can see right here, carbons would cancel out. And then we have methane right here, plus 2 oxygen gases. equals 2 water molecules and 1 carbon dioxide. So what we have is basically this chemical reaction equation here after adding all 3 chemical reaction equations. And we would do the same thing for the first one. So we're going to add this value of delta H of formation, this second one right here, and the third one. So by adding all 3, what we get is negative 802.5 kilojoules per mole. So that's basically how you can calculate delta H of reaction for a specific chemical reaction using delta H of formation. And there's actually an easier way to calculate the delta H of reaction instead of writing out the entire chemical reaction equation and then adding them all up. It's a lot easier, far easier, to just look at the numerical values of the delta H of formation. So let's do that real quick. So the first thing that you want to do here is to look at the delta H of formation values and then write it right next or right below the chemical formula. So for example, for CH4, you look at CH4 over here, it says negative 74.6 kilojoules per mole. So we're going to put that right here, just right underneath it. So negative 74.6, and again, this is kilojoules per mole. And then we can do the same thing for oxygen gas. And as you can see, oxygen gas is 0 because it's elemental oxygen. So this is 0 kilojoules per mole. And then we can do the same thing for carbon dioxide. Carbon dioxide is negative 393.5. And the last one here is water vapor, which is 241.8, negative 241.8. So now, in order to calculate delta H of formation or delta H of reaction, all you have to do is add up all the values for the products, and then we're going to subtract all the values from the reactants. So basically products minus the reactants. So here we have the products, negative 393.5 plus, and then because we have 2 moles of the water, we're going to multiply this by 2. So we're actually multiplying this by 2. Alright, so plus 2 times negative 241.8. And then we're going to subtract the reactants, which is negative 74.6. Alright. And what you get is the same thing, negative 802.5 kilojoules per mole.